Good morning, everyone. I'm Dhanush. I'm a second-year PhD student working in the Laboratory of Construction Materials with Professor Karen Scrivener. My main research area is characterizing durability of low-carbon cements and concretes. But today I'll be talking about improving early-age strength of low-clinker cements and concretes. This is because Professor Karen Scrivener is unable to make it to ACI this time. I see some disappointed faces. It's okay. I'll try my best to, to substitute her. All right, so let's start with the well-known multidimensional approach towards net zero. I'm going to show you how we can reduce the CO2 emissions in different scales. In the cement scale, we can reduce the clinker factor through low clinker blends. And there are some challenges in this scale, particularly with respect to early age strength and workability, which we are going to look at in the presentation. But when we go to the concrete scale, our focus would be to reduce the amount of cement that we use in the concrete. So this can be done through low binder concrete formulations. And finally, when you go to the structural level, we try to put concrete where it is needed. And in other words, we try to optimize the structural design through which we can also reduce the CO2 emissions. And this is the multidimensional approach. However, today we are going to talk about the cement scale and the early strength of low clinker blends. When we talk about low clinker blends, we need to talk about SCMs, and I really like this image, which shows the compositional ranges of different kinds of SCMs. They contain traditional SCMs, future and emerging SCMs. And what we, from the reactivity and availability point of view, what in our lab we work mostly on is limestone calcined clay cement, and this is LC3 as it is popularly known. LC3 is basically replacing clinker with calcined clay and limestone. And here are the common formulations of LC350 and LC335, where 50 and 35% of clinker is used, with the rest being replaced by calcined clay to limestone. And the replacements can be in different ratios, 2:1, 1:1, and so on. Okay, so first we should ask ourselves, why do we have early strength issues when we replace cements? That could be one fundamental question that we can think about. And the answer lies in the reaction degree of the SCMs when compared to cement or when compared to halite, as it is shown here. You could see here that SCMs are slow in reaction degree compared to halite. They will catch up at some point, but the problems that we face because of the slow reaction degree of SCMs is the early age strength. And here in this figure, these are the reaction degree envelopes of blast furnace slag, metakaolin, and fly ash, where the envelopes are generated from 30 to 50% clinker replacements. So you can see the slow reaction degree of SCMs can lead to low early strength issues. If you also look at the compressive strength data, as can be seen here at different ages, 2 days, 7 days, and 28 days, the LC350 and LC335 systems have very low strength compared to Normo 4 cement, which is 100% OPC, and Jura Eco 3 is a commercial blended cement. So we have issues at 2 days and even at 7 days. At 28 days, LC3 systems catch up in terms of strength development. So what we are looking at is trying to look at strategies to improve the early age strength of low clinker systems. But the main focus of this talk will be looking at LC3 based systems and looking at strategies that are employed in our lab in the form of, say, CSH seeding using commercial seeds, a combination of alkanolamines and alkali sulfates, and also a state-of-the-art grinding facility that we have in our lab. So I'll go one by one. Let's start with CSH seeding. So one solution to improve the early age strength is we can even add commercial CSH seeds that are available in the market. And the way CSH seeds work, for those of you who don't know, is that CSH seeds act as secondary nucleation sites. So they promote the formation of CSH away from the clinker particles. And what this does is that it reduces the inhibition of halite dissolution. So it can increase the halite dissolution. It can also increase the aluminate reaction. So this in turn leads to higher strength. And then the results I'm going to show you, we've used a Master X seed at 2% dosage. And these are the hydration kinetics results. For LC350 systems, the black curve is the LC350 reference system, the red curve is the LC350 with 2% seeding. You can clearly see the acceleration of the first peak and the enhancement of the illuminate reaction, the increase in the cumulative heat at all ages. So this is one way that we can improve the hydration kinetics using CSH seeding. However, when we look at the compressive strength, the results are a bit of mixed bag, because if you look at the results for LC350 reference and the LC350 2% seeding, until 3 days, the seeding results are almost equivalent or a bit less than the reference LC350. At 7 days, you have slightly better performance using the seeding, and at 28 days, it goes down, but it meets the requirement of the standard. So this is one way. The point of using the seeds is that we do have commercial solutions in the form of CSH seeds to still improve the early age hydration of the LC350. But let's go to the second solution, which is alkanolamines and alkali sulfates. Many of you who work on grinding processes might identify alkanolamines as grinding aids, because those are used as grinding aids for better finenesses of clinker. But here I'm talking about using alkanolamines as accelerators, as any kind of other accelerator when you add directly into the mix. And it's not only the amines, but also the alkali sulfates. These are also popular accelerators that people use. But it was also shown that when you add both of them in combination, both the alkanolamines and alkali sulfates, you get better acceleration. And there are many kinds of alkanolamines, but here I'm going to show results concerning DIPA, which is diethyl isopropyl amine and potassium sulfate. This is because we've done already the pilot scale studies on different alkanolamines and different alkali sulfates, and we've narrowed down everything to these two chemicals. And the way we usually optimize the system is that we have a reference system, as you can see here. Then we add DIPA in different percentages, and we also add a combination of DIPA and potassium sulfate at different dosages. And we try to see what is the optimized strength using these different dosages. Okay, so let's look at the results at 1 day, 2 day, and 28 days. So when we add DIPA plus potassium sulfate, when we add DIPA, there is a slight increase when compared to LC350, but there is a significant increase, up to almost 137% increase in strength at 1 day when you add both DIPA and potassium sulfate in combination. And if you look at 2 days strengths, it is again 75% increase when compared to the reference LC350 using DIPA and potassium sulfate. And another interesting thing is that there is no slowing down of strength at 28 days, because there is some work in literature where people have found that using DIPA or say potassium sulfate can slow down the strength. So here we don't see any slowing down of strength. So this is one interesting option. And if you're wondering about why the strength is increasing, there is lots of work that is published already, and also by Professor Franco Zunino, who worked on the mechanisms. Basically, using alkanolamines actually enhances the ferrite and C3A reaction. And this promotes the dissolution of aluminate and also promotes the formation of aluminate hydration products too. All right, so let's look at the final solution, which is the state-of-the-art grinding facility that we have. We call it FIDE Technology Low Carbon Grinding Mill. But before that, we should also look at an interesting evolution of grinding technologies. I think that ball mills have existed for more than 100 years. And the way it works is that you have a grinding medium in the form of steel balls. And these steel balls are used as grinding medium to crush the particles against the walls of the rotating mills. And this has been a popular option for decades, because it is very low relative investment, and it is also simple to use. But the problem is that the energy efficiency is very low when you use ball mills, and this high energy consumption lead to other technologies in the late 21st century, in the late 21st century, in the early 21st century, we see that vertical roller mills are used quite commonly nowadays. And the way they work is that the material is fed into the center of a rotating table, And the material is actually, through the rotational forces, distributed to these grinding areas. And then the ground material is sent to the particle separator. The finer fraction is filtered out, but the coarse fraction is again brought back to the center, and it's circulated to the grinding zone, and so on. So it happens in multiple cycles. There are many advantages with respect to vertical roller mill compared to ball mill, but there are still some issues, because since the rotational force is uneven, the particles are unevenly distributed to the grinding zone, which leads to less efficiencies and more number of cycles that are required to achieve certain fineness. Another thing is that when we have blends with different kinds of hardness of materials, it is hard to obtain an optimized size fraction when you use vertical roller mill. We also have high pressure grinding roll, where this is also a relatively new technology, where we have counter rotating rollers that can crush the cement when it is passed through in between, and it comes out like a cake. But the problem with this HPGR is that it is not used for abrasive materials, so it doesn't work for that. And what we propose, or what we have in our lab, is this FIDE technology low carbon grinding mill. And the way this technology works is the material is directly fed into the grinding zone, unlike VRM. So it is fed into the grinding zone, and you have different process settings to obtain the final material. For example, you can also put in materials with different hardnesses and get the output with a better fineness. What this does is we are reducing the number of cycles that are required to grind the material to a certain fineness. We're improving the energy efficiency, and we can also use this as a sustainable alternative, because we can increase the reactivity of the low clinker systems. We can also improve the early age strength, and so on. Well, this is the prototype that we have in our lab, which is capable of 150 kg per hour capacity. But we also, FIDE technology also have full working machines at higher capacities. And if you look at the compressive strength with the FIDE mill, you see an increase in the compressive strength at both 1 day and 2 day, as we can expect. But more interesting is the results when you look at the specific surface area versus the median particle size. The black line corresponds to commercial milling cement, and the blue line corresponds to the FIDE mill cement. You can clearly see a change in the slope, where using the FIDE mill, for similar decrease in median particle size, you see a higher increase in specific surface area. So you might wonder, why is the specific surface area increase higher when using FIDE low carbon mill? And this comes down to the SEM images. So this is the SEM image of the cement which is milled using FIDE low carbon mill. And here it is clear that there is shear fracture of the materials using FIDE low carbon mill, as opposed to traditional milling, where you have mostly impact fracture. So this is one advantage using FIDE low carbon mill, which is why you have higher specific surface area. So these are some solutions. In conclusion, I started with probably more generic solution like commercial seeds, but people who are working with LC3 systems can also explore the use of alkylamines and alkali sulfates. You can have your own dosages and try to optimize the dosages. And finally, this grinding, state-of-the-art grinding, is specific to our lab, and it is shown to improve the early age strength of LC3 systems. So that is it from my side. Thank you. If you have any questions, I'm happy to take. Thank you.